Let me introduce the third speaker. Hyun-Ho Yeo is a PhD student working with Dong-Soo Han at KAIST. So he applies machine learning to network systems, video in particular. He's doing it quite successfully. In addition to SIGCOMM', he published in Movicom and OSDI. And if you like his talk today, then feel free to offer him a job. He's graduating, and he's on the job market.
Yep. Thank you for the introduction. Hello, I'm Hyun-Ho Yeo, a final year PhD student at KAIST. Today, I'm going to talk about a system called NeuroScaler that greatly improves the scalability of neural live enhancement. Recently, live streaming has been gaining a rising popularity with the success of services like YouTube Live, Facebook Live, Twitch, or Zoom. This trend is backed by the users' surging interest in video games, interactive chats, and video conferencing. As a result, live streaming nowadays produces a huge amount of data, which accounts for 14% of the entire video traffic. Live streaming consists of ingest and distribution. First, at the ingest side, the streamer uploads a high-quality video to the media server. The media server then transcodes the video into multiple different qualities. Second, at the distribution side, the transcoded video are cached at the content distribution networks. Viewers then use an adaptive bitrate algorithm to select the best quality video that can be streamed in real time. However, there is a fundamental limitation that video quality is constrained by the network bandwidth between the streamer and the media server. So when the ingest path becomes congested, the entire downstream quality severely degrades, even if there is ample network bandwidth in the downstream paths. To overcome this limitation, neural-enhanced live streaming has recently emerged, which incorporates the advances in deep learning. In neural-enhanced live streaming, the media server uses own computations to apply neural video enhancement to an ingest stream to recover high-quality streams. Specifically, live neural enhancement consists of 3 steps: decoding a low-resolution video, applying a super-resolution network to frames, and re-encoding super-resolved frames. Such enhancements enables clients to watch high-quality video even when ingest path becomes congested, as shown in these snapshots of videos. Despite its promising benefit, live neural enhancement is too expensive to support commercial-scale live streaming. To clearly demonstrate this, we benchmarked neural enhancement using an AWS instance which has 4 NVIDIA T4 GPUs. Here, a 720p stream is upscaled to a 2160p version, where decoding runs on the CPUs and inference and the encoding runs on the GPUs. The result shows that a single instance can only process a single stream in real time. So in Twitch, there are more than 100K concurrent live streams, so applying neural enhancement to them costs over $169,000 per hour. Motivated by this limitation, we present NeuroScaler that enables neural-enhanced live streaming at scale. NeuroScalers aim to significantly reduce the cost of live neural enhancement. To achieve this, NeuroScalers answers to 2 key research questions regarding scalability. First, it effectively accelerates neural video enhancement. Second, it efficiently schedules live neural enhancement on a large cluster of GPU instances. Before diving into NeuroScaler's design, I'll first analyze the bottlenecks of live video neural enhancement using 2 Straman approaches. The first Straman runs super resolution frame by frame. Using the same experiment setting as before, we measure the number of streams that can be processed in real time per instance for each processing in isolation and the end-to-end pipeline. The result shows that only a single stream can be processed in real time because super-resolution inference is too expensive. The second Straman applies selective inference. In selective inference, a super-resolution DNN is applied to a fraction of frames, which we will call as anchor frames. For other non-anchor frames, previous super-resolution ALPs are reused based on codec information. Selective inference is carried out in 2 steps. Before running inference and reuse, an algorithm first selects the most beneficial anchor frames within a video, which is critical for maximizing the benefit of selective inference. So by applying selective inference, SR inference throughput becomes 10 times faster, but end-to-end throughput still remains the same. So which processes become the key bottleneck now? First, the latest anchor frame selection algorithm, NeMo, is designed for on-demand video, which requires per-frame inference to estimate the benefit of anchor frames. However, this is infeasible in live streaming, where anchor frames must be selected on the fly. Otherwise, naively selecting anchor frames, like uniform sampling, eliminates the costly selection, but largely diminishes the benefit of selective inference. Next, super-resolved frames must be encoded in real time for distribution. However, compressing 4K 60 FPS video is 2.5 times slower than selective inference, even with the on-chip hardware encoder. Even worse, hardware codecs are often unavailable on many accelerators like GPU or FPGA. In such a case, video compression using the software encoder becomes 5 times slower than the selective inference. In this work, we chose to extend the selective super resolution, the latter Strawman, and resolve the main computing bottlenecks. To do so, NeuroScaler introduces novel system components. The first component, Zero-inference anchor selector, chooses anchor frames without any neural inferences. The second component, hybrid encoder, optimizes video compression for selective super resolution. From now on, I will explain each system component. Our Zero-inference anchor selector chooses impactful anchor frames without any neural inferences. We enable this by leveraging a key observation that the benefit as an anchor frame critically depends on 2 types of codec information. First, frame type is a primary factor that determines such benefit. A compressed video consists of hierarchical structure frames, and they are special type of frames that have a high degree of dependency to other frames. For example, in a VP9 codec, key frames and alternative reference frames belong to such types. Those frames deliver a larger quality gain as an anchor frame because super resolved outputs are directly reused by many non-anchor frames. Next, among the same type of frames, the benefit as an anchor frame is largely affected by residual, which is the temporal difference between frames. In selective inference, an error is inevitably accumulated across non-anchor frames because reusing super resolved results is not perfectly accurate due to residual. The error resets at an anchor frame where a super resolution DNN is applied, so this anchor frame reduces the total error by a yellow colored area. This indicates that an anchor frame delivers a larger quality gain if it clears a larger error. In addition, this error can be approximated by accumulated residual, which details are described in the paper. So based on these observations, the selector operates a multi-level queue using a frame type and residual. The selector divides frames into groups where each group consists of the same type of frames. Second, for each group, the selector sorts frames by their accumulated residual. Lastly, the selector picks anchor frames from the highest to lowest priority queue within an available computing budget. These processes are periodically invoked during live stream. Zero-inference anchor selectors rely on codec information, which can be easily extracted, so it can process 100 streams per CPU thread, while the latest method, NeMo, cannot run in real time on CPUs. At the same time, our anchor selector delivers a similar quality gain compared to the baseline method. Next, our hybrid encoder re-encodes super resolved frames in real time by synergistically utilizing both an image and video codec. The hybrid encoder reuses an ingest video to store non-anchor frames in low resolution, and compresses only super resolved anchor frames by running an image codec frame by frame. That is to say, a hybrid encoded video consists of high-resolution anchor frame and low-resolution non-anchor frames. Image compression is much faster than video compression, and the hybrid encoder applies such lightweight compression to a small fraction of frames. So when measuring encoding throughput on server-class CPUs, hybrid encoding is around 81 times faster than traditional video encoding. Next, non-anchor frames are directly sent at low resolution, providing a large room for encoding anchor frames. At the same time, anchor frames are located sparsely, so image compression does not severely harm compression efficiency. As a result, hybrid encoding provides comparable compression efficiency compared to traditional video encoding. So far, we have talked about two primary components which accelerate your enhancement. There are two additional components in NeuroScaler to support multi-instances and multi-streams. Anchor-level load balancer accurately distributes anchor-enhancing tasks on a cluster of GPU instances. Context switching optimizations reduce overhead in processing multiple streams on a shared GPU. Please refer the paper for the details of these components. From now on, I'll introduce evaluation results regarding throughput, cost, and quality. During the experiment, we used top 6 Twitch contents, such as League of Legends, Minecraft, and so on. We applied a DNN from NAS to upscale a 720p 60 FPS live stream to a 2160p counterpart. We encoded super resolved frames using a VP9 video codec and a JPEG 2000 image codec. This process was executed on AWS G40N 12x large instance, which has 48 vCPUs and 4 NVIDIA T4 GPUs. Next, we compare NeuroScaler with two baselines: per frame SR that applies per frame super resolution and video encoding, and uniform SR that applies selective super resolution to keyframes and equally spaced frames and encodes the outputs as above. To demonstrate throughput improvement, we measure the number of streams that can be processed in real time under the same quality and the same instance. For each baseline, we tested the performance on two cases, where a hardware codec is available and unavailable. Note that the NeuroScaler's hybrid codec does not depend on specialized hardware features. And this is the average results across the 6 videos. NeuroScaler can support 10 concurrent streams, which is up to 10 times faster than the baselines. In contrast, the end-to-end throughput of per frame and the selected baselines is constrained by the inference and the encoding throughput, respectively. NeuroScaler's benefits becomes larger when comparing costs using a cost-effective instance for each approach. And this is the average cloud computing cost per stream per hour. NeuroScalers can reduce the cost by 22 times compared to the per frame baseline and 3 to 11 times compared to the selected baseline. Since NeuroScaler largely reduces the GPU and CPU usage, it can run on more economic instances which have fewer GPUs and fewer vCPUs. Lastly, we demonstrate super resolved video quality in PSNL across the 6 videos. NeuroScaler delivers a large quality improvement ranging from 1.7 dB to 7.3 dB. So, to sum up then, I have talked about 3 things. First, NeuroScaler is a framework that improves the scalability of live neural enhancement. Second, to enable this, NeuroScaler introduces several novel system components. And finally, NeuroScaler delivers a significant cost reduction in live neural enhancement. Thank you for your attention, and I'll be glad to take any questions.
Questions? Yes, Henning.
Thank you. You alluded to it a little bit, but I wanted to make sure I understood. Most of your video examples were Twitch video gaming type applications as opposed to Zoom or interactive, two-person video type of application. Was that intentional, or is that where most of your upscaling is done?
Actually, the design of the NeuroScaler is applicable to any type of live streaming, as you said, live video conferencing. But we tested our system on Twitch contents because we need a high-quality video, 4K 60 FPS raw video. So we test on those type of streaming services.
Okay. Because, I mean, video content generally, game content, because it's generally artificially generated as opposed to naturally generated, seems easier to scale up because it often has more defined boundaries and all of that. So did you see any difference in performance between the two? I mean, like perceptually in terms of...
Oh, yeah. As you mentioned, actually, the difficulty of the super resolution is a little bit easier for game contents we have seen because, the natural scenes like seen in the video conferencing contains much complicated artifacts, and yeah, performance is a little bit lower than the when you test it on the game, but it still delivers a significant benefit in terms of PSNR, maybe higher than 2 or 3 dB. Yeah.
Yeah, we have a question over here.
Yeah, hi. Thank you for your presentation, as it is very good work. So I have two questions. The first question is, because you're a hybrid encoder, right? So how about the decoder? Because it's hard to do that, in my opinion.
Yeah, and so I'm going to explain how hybrid stream is decoded at the client side. So when a hybrid encoded stream is transmitted to a client side, the decoder first checks whether it is an anchor frame or not. And if it is an anchor frame, actually it decodes and caches in memory. And otherwise, it decodes and reuses the previous super resolved frames. And we tested this hybrid decoder on mobile phone and measured the throughput and also measured the power measurement. And actually, it incurs a little bit overhead, around 20 to 13% compared to the traditional decoders. But it still can decode 4K video even with the commercial smartphone.
Yeah. Okay. So when you deliver the data on the network, so you just have two streams. One is to delivery like the image, image encoding content, and another is video decoded content.
Yeah, it can be seen as two separate streams, but in our implementation, we actually package the anchor frames and non-anchor frames in a single, frame, encoded frame.
Okay, thank you. And can I ask another question?
Please.
Yes. And I have read your Livnas work and Livnas from SIGCOMM'22.
Yeah.
Yes. And in that, you have do the online training, right? So how about for this work? Because if it is a live streaming, so the scenario of the contents is changed. So how to fix it in this scaling environment?
Yeah. As you said, actually, in live streaming context, we need to update model online to mitigate the data drifts. But in our work, we could focus on the inference side because we observed that the inference is much expensive than the training, because training can be, optimized by leveraging the similar contents previously trained over on the past. So, and actually, we also design a module called context switch optimization to support, the online updated models. Yeah, we have such components to deal with that, but we haven't, tested our framework on while really updating the model on the fly.
Okay, thank you very much.
Yeah, I have a quick question. So video is complex application, and you evaluate NeuroScaler in terms of PSNR, right? What about other metrics like VMAP, SIM?
Oh, yeah. Actually, we also tested our system using VMAP, as you said. Actually, this is a quite popular video quality metric proposed by Netflix. And when you test VMAP, its score is ranging from 0 to 100. And the original streams, the score is around 40 to 6. And when you apply the NeuroScalers to those streams, the scores improved to around 80 or higher than 80.
Okay. Okay, so let's thank Hyun Ho for the presentation. And wish him good luck on the job market.